Hello and welcome to this interview at Digital Foundry with the developers of Alan Wake 2, a game we've come to love here at Digital Foundry this year for its incredible graphics and really interesting narrative elements. And today I'm joined by two people who worked key positions on the technical side of the project to talk about how it runs on consoles, PC, and what they did to make this project possible. So before I get into the meat of the real questions here, I would love you, Tatu and Antti, to describe your role on the project individually and what you exactly did.
Yeah, I can start. So my name is Antti Kerminen. Hello. I have been the technical director on Alan Wake 2 from the beginning. And before working for Alan Wake 2, I was working on Control and on Tatu's rendering team. So that's my immediate background for that.
And I'm Tatu Aalto. I'm leading the graphics programming team at Remedy. I've been here since 2011.
Okay, so just like Antti just said right there, moving from Control to Alan Wake 2, what were some things when developing Alan Wake 2 that you needed to make the project possible in the first place? Some core tech things that Northlight needed to have changed to make Alan Wake 2 possible. And another thing is, what other things were added into Northlight during that time period that essentially eased and made development possible?
Yeah, so maybe I can start.
Go ahead.
So one of the things that was very specific to Control was that it was happening indoors. So inside a building, very special building, supernatural building, but still you didn't have like a long view distances, and the number of objects that you had on the screen at the same time was quite limited. But on Alan Wake 2, we moved to outdoor environments and especially to the primordial rainforests of Pacific Northwest in the USA. So we needed to draw a lot of geometry to the screen because you have a lot of vegetation, trees, bushes, whatnot, and long view distances. And I think that one of the biggest enabling features was that when we moved in our rendering engine to fully GPU-driven rendering pipeline. So that allowed us to get rid of some of the overhead that you typically have when in a rendering engine when you draw individual meshes. So now we don't have that overhead on the CPU side anymore, and you can do more accurate culling for the geometry. So you can have more geometry in the scene, and you end up drawing less. Optimally only what you see, but a bit extra, but you can do much more accurate culling there. So that was definitely one enabling feature that supported the game's vision. And slightly related to that, we knew that we are going to need more game objects or entities in the scenes and on the levels. And we knew that our old game object model had some overhead for all the entities. So we moved to entity component system for our game object model, which is quite fashionable nowadays among game developers. But there we got rid of much of the overhead that we had in the old system. So we have just pure data that the entities are composed of components, and also like an efficient way of multi-threading and updating them. That was important for streaming speeds also, because in our old component system or in a game object system, creating new entities took quite a lot of time, and that was throttling the streaming speeds. So now we can create new entities on the fly more easily, and we can take better advantage of the modern SSD drives. And also, like it helped a lot to make the game better multi-threaded. So it's more easier to write safe multi-threaded code, and that is efficiently multi-threaded. So definitely our engine scales better to multiple entities in the scene. We actually moved also to new scripting language. That was one enabling factor. We had our own custom scripting language. It was quite limited in its capabilities. So we moved to completely kind of complete programming language Lua, and then further Luau that has been developed at Roblox, which is like a further derivative of Lua. And then that kind of empowered the content teams to create much more on their own. So they could iterate and implement stuff without programmers. And it supported full hot loading and live editing so that we could have the game running and people could write and debug their scripts while the game was running. So definitely allowed us to do much more. And to be like completely honest, like moving to kind of ways of working where the content teams create more with a full-blown scripting language also had its challenges. So I would assume that one of the feedbacks that we got was that they would have appreciated more programming support to kind of adapt that scripting language. But definitely like the net effect was positive. We were able to do more with the help of Lua.
So with Lua being in there, did you find that having such a dedicated scripting language worked against the efforts to have the engine be better multi-threaded since the control times? Was there some tension there?
Yes, exactly. Like everything that's happening on the script side is single-threaded, but we are just limiting that part of the frame to a very small amount so that there's a small section of the frame that is single-threaded that is running the scripts. And that's only like one location or one section of the frame so that we are not destroying the multi-threading over the core in several places. So that of course like poses some restrictions like on what you can update and how quickly you can see the response on screen. So that poses some restrictions. So it's you can't achieve like everything. Like there might be some delays on some effects, like one frame delays or something like that when you have like only one place in the frame when you can do the script calls.
So you described an update to multi-threading there. Could you be a little bit more specific on the multi-threading model that the game is using?
So when we are talking about the entity component system, we are talking about multi-threading for the CPU workload separate of the rendering thread. So these two things are still separate. But inside that CPU workload, we have ways to define what data are you reading and what data are you writing. So you don't really need to care about how that's being multi-threaded when you are writing the gameplay logic. You just define what data you are reading, what data you are writing, and then that gets parallelized. So that's kind of easy way to ensure that the data access is rate safe.
Tatsu, would you like to add anything to that actually?
Yeah. The rendering situation from the rendering point of view, we have been kind of like separated threads already in Quantum Break completely, so that we are running gameplay stuff on other side of the threading and the rendering on other side of the threading, and it goes so that the gameplay and all other systems are kind of like feeding data to rendering side, and rendering is then completely independent.
Mm-hmm.
And the design decisions on the GPU drawing, they are such that we've been actually, to be honest, we've been suffering on CPU side cost since basically Quantum Break. We've been basically filling almost all the threads that we have available by just making draw calls on many threads. So that's it's a huge bottleneck. And I mean, it's been getting worse over the years. In Control, it was relatively bad already. We did quite a big effort on optimizing it, obviously, and it runs fine in the end. But we were feeling quite a lot of CPU time from them, just basically doing draw calls.
Oh wow!
So yeah, originally I remember Art Folks coming back from the photo shoot and giving me a map of Alan Wake's, kind of like, okay, here's a map. It's 5 kilometers, 10 kilometers by 10 kilometer, and there's going to be a lot of forest. So it's pretty obvious that this is not going to be scaling. with what we have in Control. So that was kind of the point that we have been thinking about this for quite a while. Now at this point we had got rid of the old generation consoles and also kind of like restricting us to more modern GPUs on PC side. So it was relatively easily possible at this point to actually make a flip and just go fully onto GPU side. And yeah, that basically took rendering, which has been very multi-threaded on the rendering thread side. We have kind of like a main thread, which has been pulling more threads to jobs to make draw calls. So basically this infrastructure made us actually get back to single-threaded because we don't really use CPU that much for doing draw calls. So it is just in simple one thread on CPU side, which is nice. It's less complex and it's faster.
Okay, so you just talked about making the game run on more recent GPU hardware and focusing on that. And a big part of Alan Wake 2's release was that it was one of the first games that we've seen that had, I would say, more explicit support for mesh shaders, particularly on the PC platform, where we did some tests looking at Pascal generation GPUs as well as RDNA 1, which doesn't have explicit mesh shader support on PC at least, and we noticed some big performance differences there between those GPUs that lack the mesh shader capability and those that have it, that are more recent GPUs with more modern architectures. And I would love to know essentially at what point in the development project was the decision made to kind of limit the game to be using mesh shaders, to use mesh shaders in such an integral way, and essentially what was the design process like on utilizing mesh shaders for Alan Wake 2?
Well, we didn't actually exactly limit the Alan Wake to be mesh shaders only, so we have vertex shader path also. Mesh shaders were picked just because of nicely uniform support on the platforms, on the console platforms and the PC that we are running, and then by the fact that it's possible to do more fine granular culling, since we had a lot of vegetation in Alan Wake, and we know that it's going to be very dense, and the meshes are going to be relatively large, so that doesn't fit very well for culling per object. Basically, the setup is such that you have a lot of alpha tested stuff where you can see through, and you have a lot of meshes which are relatively big. These forest scenes that we have in Alan Wake, the biggest trees are 20 meters high, even higher maybe. I don't actually know what's the current situation. They have been going back and forth. But anyway, they're huge meshes. So if you kind of like start culling per mesh, those are going to be visible almost always. So you need to subdivide them somehow. And mesh shaders seem to be something that were supported on almost everything that we wanted to run. So it was kind of like natural to take that as a kind of like the basic building block for going forward. It's also supported on the current generation consoles, so that's kind of like the low end for the kind of or baseline for the stuff that we do now, since the previous generation was dropped out. If we had, of course, done it for the Xbox One then and PlayStation 4, then that would be a different thing. But yeah, we concentrated on making the culling working smaller pieces.
Okay, so it sounds like meshlet culling being the primary usage of the mesh shader on the platform supported. But I'm very curious, was there any specific research and development beyond that? Because if you look at the game world, there's a lot of very highly detailed, dense geometry on the ground close to the camera did you look into tessellation or any form of continuous LOD as a part of the development for mesh shaders in Alan Wake 2?
Well, we did height field rendering for Alan Wake, so that's the kind of like the base of everything that you see in the game. To be honest, I mean, most of the locations are propped with meshes so that you don't see that much of the base ground, which is dynamically tessellated. Yes, it's more dense, close to camera, but it gives a nice kind of like seamless backdrop to build on top of. But we don't support any kind of like dynamic tessellation of meshes themselves. So we have a lot of photogrammetry meshes in Alan Wake, and of course this is kind of like increasing trend on industry that there's a lot of photogrammetry meshes, and those tend to be so detailed already that you usually don't need to tessellate those in game content. I mean, in some specific cases, close-ups and that kind of stuff, but usually when you photoscan stuff, the meshes that you get out from the scanning, they are very detailed already. So you mostly want to get rid of some of the geometry by LODing less detail.
Okay, so you mentioned the current generation consoles, and on PC and Xbox Series consoles, you have explicit DirectX API support for mesh shaders. But on the PlayStation 5 side of things, you have a completely different ecosystem there, similar GPU to a degree. I'm curious, was there any sort of balancing act in the development of Alan Wake 2, specifically with regard to mesh shaders, that had to be done to kind of cover all bases and make sure that it ships feature complete on all the platforms?
PlayStation is actually very close to PC specs, so I don't think we didn't do anything specific to meshlets really. The meshlet sizes are slightly different on platforms, but that's basically conversion time stuff. So not really. Obviously, there has been a lot of platform-specific optimizations, but those are not so much specific to PlayStation or Xbox or AMD or NVIDIA, but they are kind of like general optimizations that help. Usually everything, all the platforms, and some of them happen to work a bit better on some platforms than other ones.
Okay, now let's move away from geometry, which we've been talking for a bit, and talk a bit about lightings, because in Alan Wake 2, the game, a lot of the scenes in the game are just primarily lit by indirect lighting. If you look at any of like the forest scenes of the game, any of the indoor scenes that don't have a lot of artificial light sources, particularly when you're playing a saga, they're almost entirely indirectly lit. And on PC, you obviously have two paths. You have a ray tracing path and then something else. So if you could please actually describe how indirect lighting is achieved in Alan Wake 2 without ray tracing.
Yeah, so the basic backbone of everything is baked GI, as we have in Control already, and also in Quantum Break, actually slightly different flavor, but anyway, the backbone is baked GI. So we have a couple time of day setups in levels which we can switch between, and we have kind of like art directed loops for those different time of days, and that's then kind of like the baked solution is then backed up or made more dynamic by screen space reflections and SDFs and then ray tracing.
Awesome. So on PC specifically, where you do have access to the ray tracing path there to do indirect lighting, I was curious how that ray tracing slots in with this other system you're describing of doing baking. Because in some scenes in the game, you could see them seemingly intermingling together, but in other scenes, for example, like whenever you're in the forest with very different lighting conditions, usually it seemed to almost be wholly done by the ray trace lighting. So I would love to know how that kind of balance was achieved, and was it like a fully artist-driven decision? How is it done exactly?
Yes, it's mostly art directed stuff. Uh, the setup is such actually that we have some of the direct lighting is baked into the GI, and in those cases we don't have capability of making it runtime dynamic, and that's the reason why some of the scenes which have been kind of like artist authored with the baked lighting, they don't react to all the dynamic changes, and the accuracy of the lighting is slightly less than what you get with for instance ray tracing, because you obviously can't go to millimeter detail on the baked solutions. You just run out of storage space and memory. So it's a balance basically. The baked stuff is very accurate in light transport. These are bakes that we are baking overnight or hours, and you can, with those, you can actually create kind of like a lighting setup where you have let's say you have a house and you have a bright scene outside and you have a small hole in window, and you can actually use that kind of setup to light the whole interior scene. And that kind of setup is next to impossible still to actually completely resolve in runtime, because it's very expensive. You kind of need to do the whole light transport stuff and find that small hole in the window and then distribute lighting from there. So some of these setups are so complex that we didn't even try to make them fully runtime dynamic. They are baked, and that's the reason why they don't react to all the dynamic movement in the same way. It's a trade-off. This is kind of like it's very cheap way to also achieve kind of like a very complex lighting setups.
Yeah, like you're describing, like if you have a small cabin with just a tiny window cut out in it, resolving lighting in real time there, even with great path tracing, is going to be expensive and will require a great amount of denoising. So I can get that decision completely. But getting over to more specific aspects of the ray tracing, you described those sections with Saga earlier, where on PC, when you have path tracing enabled, for example, and you look far into the distance, you can see that all those reflections are actually still there, really far into the distance. So how exactly are you managing the BVH in the game to enable good performance at the same time as having all these things covered by path tracing?
Well, to be honest, it's relatively expensive. But yeah, the entity counts we have in the game, they are very large. The amount of geometry and amount of kind of like dynamic movement isn't that big of a problem. It's more the fact that it's divided into so many small pieces, and the PVH builders that are currently in DX, they just don't handle very nicely that kind of load. So we are kind of like in not in a sweet spot of kind of like doing big meshes with a lot of geometry. That's usually fine. Then doing very trivially small pieces is fine, but we are kind of like in middle ground, and it doesn't work very very nicely with the current PVH building. So we ended up kind of like staggering the updates. So we basically update further bullets, further moving objects on slightly less frequent updates. It basically goes so that everything close to you is updated always, and all the important assets like players and enemies and that kind of stuff, that's updated all the time, because otherwise you would see flickering on those. But then all the rest is kind of like in 5 meters, things start updating every second frame, and in 15 meters, it's every third frame, and so on. I can't remember the exact meters. To be honest.
You don't need
but
to.
anyway, you get the point.
Yeah, I mean, even if you are staggering the updates there, you don't really seem to notice it in the game, or at least I didn't notice it while playing in any of the scenes. It must be just like the intervening geometry as well as just the size and pixel size and screen space doesn't make it at all obvious that that is even occurring at a distance. I didn't even notice that. Okay, so what are the considerations actually for the things that are included in the BVH? Is just everything included outright? Is there some sort of tag up? Are some things not ray traced against on purpose because they wouldn't look right if ray traced against? How is that exactly done?
We actually ended up pushing everything to ray tracing. That was kind of like it was discussed multiple times on how do we actually manage the amount of objects in there. But there was basically two choices. You either choose only objects which are close by, or you only choose objects which are important, or then you put everything in but don't update it always. And we opted to go with just having everything in but don't update it quite as frequent. This is basically driven by the fact that we are doing restir from all the lights, and you kind of need to have all the geometry because there can be far by objects behind the player which actually cast shadows and that kind of stuff. So if you start taking anything out from the BVH, then you will start seeing artifacts from that very easily. And it's also simple as a setup. It's if you take something out and you still want to do shadows, then you need to combine ray tracing with shadow maps or something like that, and that's kind of like a hassle, and it kind of loses the nice look of the mix of the soft shadows and hard shadows and that kind of stuff. So we went this way this time.
Okay, you did just mention it, but I would love to know what is being done to manage noise on the sampling level. Essentially, you did say restir, but what are the techniques being used in the game to manage noise pre-denoising, essentially?
Yeah, we use algorithm called restir, which is developed originally by NVIDIA. So it is a method of wisely choosing the light that contributes the most for each pixel. It's basically spatial, and then it has some sort of a heuristic of what light you should consider for some certain pixel. It's very noisy signal, and it does need to be denoised, and we have many denoising methods available. We have couple done by ourselves, and then we have some denoising methods from NVIDIA also.
Yeah,
and some of them are exposed directly in the game options.
Yeah, those options are kind of obvious on PC. You can see them right there in the menu. Okay, but getting one last question about ray tracing here, then I swear I'll go on to something else. But on Control, when you shipped the updated version for Xbox Series X and PlayStation 5, you did ship ray trace reflections there, transparency, and opaque. And I would love to know at what point during Alan Wake 2's development did you decide you would not be shipping hardware ray tracing on the consoles this time around? It was there in Control, and then Alan Wake 2 obviously is a completely different game with very different resources being allocated to it in the rendering, but it wasn't there in Alan Wake 2. So I'd love to know exactly when and how that decision making occurred.
We did the decision relatively early, actually, to be honest. Kind of wanted to pick our battles at some point. It's as I said, the BVH building on Alan Wake it's expensive. We have a lot of dynamic geometry, and we did know already like year before the launch that it's going to be heavy, and it's going to require major effort to actually make it run even on PCs nicely, and just kind of like counting amount of days and what can we actually polish in this time. just did not adapt to actually supporting all the platforms and even trying. So yeah, we fortunately did the decision relatively early. So we didn't waste huge amount of time actually chasing something which was not at all certain that we could actually achieve.
Yeah, that makes a lot of sense. And now I swear this is going to be the last ray tracing question, but I just thought of it as you mentioned it again. Okay, you described that the BVH is very heavy, and you're kind of at the limit there with what the API and even the hardware can really bring to the table. And I would love to hear from your perspective as developers, where you would actually like to see the APIs and hardware go in the future to make this BVH problem as a part of ray tracing's whole better, more performant, more manageable. What would you like to see done there?
Well, the BVH building is definitely the one kind of like from the API standpoint and from the algorithm standpoint, which has not seen a lot of love from anybody actually after a launch of ray tracing on DX, for instance. So that's definitely a bottleneck on many things. It's relatively hard to configure for running LODing setups similar to Nanite, for instance, and it is not performing very well. So we are actually using quite a lot of time on CPU side to just submit. We don't submit any more draw calls, but we submit quite a lot of BVH build requests on the CPU side because GPU API does not exist. It's the only way to actually feed the BVH builder. So that's definitely something that does need to change at some point. So there needs to be some advances on that front.
Yeah, and correct me if I'm wrong, but isn't it also a question of hardware capabilities? So kind of originally the GPUs were for drawing or rasterizing things, and building BVHs is a bit different kind of workload and different kind of computational problem to solve. So I think that in order to make that more efficient, that might need like then different kind of hardware support also.
Yeah, sure, definitely also that. Yes.
Those are all very reasonable takes, I think. Okay, Antti, at the beginning you did mention streaming very specifically and enabling the game to utilize it more. We, while looking at PC, we haven't published anything about it, but other people have. It's like CompuSemple, where they've looked at the game and they see that it does give actually a pretty great workout to modern SSDs. And I would love to know essentially the concept behind how streaming is done in Alan Wake and how it enables the experience. Like, when is it occurring and what is it doing?
Well, there are different things that we stream, and there are several of them. So we are streaming texture MIPS, so that we have a fixed size of pool of memory, and then we stream in and out textures in different levels of detail based on the need, what needs to be shown in the camera. And then we have a similar concept for meshes actually, so that we are streaming in and out LOD levels for meshes, that we are streaming out stuff that we don't need and then stream in more detailed meshes when we need them. Then additionally, we also have hierarchical LODs, so that we pre-process the scene and we can set up some scenes or some sets of objects to be processed so that we collect individual meshes and group them together and then calculate an LOD for a group of meshes. And we can do this in a hierarchical manner so that we can take these group meshes and then collect them into even lower detail groups. And these can be also then streamed out. So these are, for example, used for buildings. So you have a building inside of which you have a lot of objects. But then you can stream out the individual meshes and just have like a course level LOD for the whole building, and the interiors are not streamed in anymore. So these are being streamed in. And that's not all. Then we are streaming entities, and there are different ways to stream entities and levels. So some of the entities are streamed based on distance. Prime example would be the grass blades. So they are just streamed out in distance. And then we are scripting, like we are manually scripting some of the streaming for entities. So that a good example from the development times would be that when you are going in a dark place to the subway tunnels, you can stream out what's on top of the streets, so on. But that's all like manually scripted. That we are just streaming out stuff or entities that we don't need on that specific location. And then we are doing, under the hood, we are doing some background processing for all the streaming requests. So when we know that we are not going to need some assets, we are actually batching those requests,
right?
Read requests for the data, and then try to make that as fast as possible, the file reading.
Right.
And we are also caching some of the assets, so that if you have some recently used assets that properly found from cache, and you don't have to actually read that from disk. So there's a lot of stuff happening in the background whenever you move the camera and move the player. So there's a lot of processing happening in the background. So in order to utilize the SSD speeds that are available nowadays, you need to see trouble to organize the engine so that you can actually receive the data with the speeds that are possible nowadays. And you need to be, of course, able to run the game at the same time. So most of the processing power goes to updating the game and then receiving the data in the background with high speeds. That requires effort. So the SSDs are so quick nowadays.
Did you, as a part of this, at least on the PC and Xbox side of things, did you look at utilizing the low-level, like direct storage access to make that much easier and cheaper?
Yes. So that's related to batching the file reads and so on. That's related. That can be utilized by direct storage also, and that's related to that. So yeah, we are trying to utilize that too.
Okay, so we're gonna start with PC, and then we're gonna go to Series S because they're slightly related. Memory is just on PC you have a lot more memory, but it is split into different pools, something that you don't have to deal with on the consoles. And so how do you manage that specifically on PC to make sure you aren't just thrashing the PCIe bus all the time?
To be honest, I don't think that we take any specific measures for that. It's just a way to pool the memory differently, so that you have like that dedicated GPU memory on PC, but it's just a matter of like pooling the memory differently, and we don't have like any specific measures to deal with that.
But we of course try to limit the amount of data in all the possible ways. The most important part is of course that you don't push stuff that you don't need on GPU. So that's the guiding principle. It also makes everything more fast. You don't have extra waste. It's actually relatively expensive to copy memory all over a place.
Yeah, and of course we are conscious about using the memory bus when we are copying data from CPU to GPU, for example. So that's we try to be efficient on that sense, of course.
So now in the opposite direction, Series S, Alan Wake has incredibly highly detailed textures, extreme geometry. It has SDFs. It's got a lot going for it that would make the limited RAM pool in the Series S big trouble. So how was the game scaled exactly to Series S? And it turned out really great in the end. There was a lot of nervousness about Alan Wake 2, but the Series S version is pretty great. So what was that like?
We did spend some time on optimizing for Series S, and it required a lot of work to make that possible. And I think that the big kind of limiting factor, whether you can pull it off or not, was more limited memory size of the Series S, because that's kind of a hard limit. You just have to fit under the memory constraints, and for that we spent some time. So it's also a bit more difficult than performance, because there are not so many options to scale the engine to a small amount of memory. And one of the main things was actually to shrink the texture memory pool, so that then we let the streaming to handle the fact that we just get as accurate textures and as detailed textures as possible streamed into a more constrained memory pool. So usually we have about 3 gigabytes of texture memory, but on Series S we have only 1.2. But it works surprisingly well, because we are also rendering at lower resolution. So when you have a slightly smaller resolution, you don't need to have that detailed textures streamed in. So they go hand in hand, and they both save some memory, because with a smaller resolution, you can have smaller rendered targets on the rendering engine, and there are multiple of those. So together those save considerable amount of memory. And then we have a bunch of small optimizations or quality optimizations that then save either memory or then processing time. And then when you combine that, after quite many profiling and optimization passes, we got the game running nicely on Series S. And it's true, it was actually quite often mentioned at the office when people were trying on Series S that the game looks actually surprisingly good on Series S optimizations.
Yeah, it worked out very well in the end. We were pleasantly surprised by it, because there's been some games have been more elegantly scaled to Series S over the generation so far, but other ones you've seen where it kind of required like a big axe to get it working in the first place.
I can kind of imagine that might be something to do with time pressure and needing dedicated time for that.
Yeah, that I can imagine too. So this actually wasn't originally on my questions here, but since we are getting towards the end of the amount of questions I had, recently the game just shipped a new patch. Adds a lot to the game, but you also very specifically called out GPU time savings for the console versions in the patch notes, which is a pretty rare thing to see, and I loved it. Can you explain a bit about how some of those milliseconds were won back after launch?
Satu can make a compliment that, but I think that we specifically made the GPU side culling like more accurate, that we are utilizing in the first place. But it's of course like a new feature, and we already knew when we shipped the game that we can improve on that, and then we luckily got that work completed after launch.
Yeah, we have, of course, I mean, we did pull huge amounts of optimizations close to launch, and we have a long backlog of all kinds of optimization ideas in the backlog. And some of those were kind of like low-hanging, relatively close. We didn't quite make them for the launch, so we are trying to package the ones that make sense at this point still the future patches.
We have a lot of geometry in the scenes, so if we are able to make like optimization that reduces the amount of geometry that we push to the GPU, it can have like a big effect on actually the frame rate.
Yeah. The biggest optimization was to make the occlusion culling indeed slightly more accurate. There's some smaller ones also which are coming in, but I don't think we actually raised them even to release notes most likely. usually because they are kind of like small ones and they help on some specific situations, for instance, and so on. But yeah, this one is relatively big and affects pretty much all of the places.
Wow. All right, so we've gotten to the end of my explicit questions, but I'd love to hear from the both of you, Tato and Antti, exactly. I always love asking this question, but what were some things on the project that you were really proud of working on, or just some aspect of the project? It doesn't have to be some specific thing, but what was something that really made you happy when you were working on the project?
I think the setup was fun. It's kind of like the control was very different kind of game or very different kind of setup than Alan Wake. So it was a very nice change to do this kind of like outdoor locations and lots of moving foliage and that kind of stuff. I think that was fresh for us, and also the creative vision which was done for the Alan Wake had so much, all kinds of things. It's interesting in many ways. Also making it is interesting in many ways.
Antti?
Yeah. I have been in the project from the beginning and also working in the leadership team of the project. So I kind of naturally think of the whole, and I kind of concur with Tatu that the creative vision was very strong on this project, like very compelling and inspiring to work with. Right from the beginning, this was a project that has been like long on Sam's head before we kind of officially started the project. So the creative vision was kind of well matured when we started this project, and that carried the whole project along the way. And it was, for me, like kind of the best part of like making games is to kind of see these compelling creative visions to come live, and we really achieved that. I think that the end result is maybe the closest to the original creative vision I have seen before, and like just having the technology being part of that and enabling that, I think that has been the most kind of uplifting or kind of inspiring thing on this project.
Yeah.
That's well said.
Yeah, very well said. And I gotta agree. It is, of all the games I've played this year, it's the most unique and the one where you can definitely see that it was planned out meticulously in every detail in every single scene you're in, from like the little bits in the Oh Dear Diner all the way out to like the expansive views when you're playing a saga. So it's beautiful, and everyone should be very proud of the work they've done. Definitely. And we definitely appreciate also you talking to us about it, because getting behind the scenes information about a game that does so many new things in rendering is pretty rare. And I don't know, do you have any GDC or SIGGRAPH presentations lined up for the future?
We definitely have as a company. So there are people going to be presenting stuff at GDC, but I don't know if they are rendering related talks.
We have talked about skinning and building the large scale foliage stuff in GDC Summit.
Okay, great.
And there's some other ones maybe coming also, but those are not confirmed yet. But Kia will do a very nice presentation about the foliage stuff in GDC.
That'd be awesome. I look forward to it. But okay, Tatu, Antti, so grateful for this. Thank you for talking to us today about it.
Thank you.
Thank you
Having us.
Always lovely to discuss with you.
And of course, for everyone watching in the audience here, because I would love to edit this video up, of course. Have a great rest of the year. Merry Christmas, Happy Holidays, and we'll see you next time on Digital Foundry.